Welcome to my channel, e-learning.
All right, let's talk about one of the most incredible, most complex pieces of biological engineering in the known universe, the human eye. But first, let me ask you something. What if I told you that right now, as you're looking at the screen, your eyes are actually seeing the world completely upside down? Yeah, seriously. Stick with me because how your brain fixes that is one of the coolest things you'll ever learn about your own perception. Okay, so to get how vision works, we have to start with the tiny things called receptors. Think of these as little specialized sensors all over your body. They're designed to pick up on one specific thing from the outside world, like light or sound or heat. And we've got a whole team of them. You've got thermoreceptors that tell you if your coffee's too hot, mechanoreceptors for touch, chemoreceptors for taste and smell. But for today, the absolute superstars of the show are the photoreceptors. These are the ones built for one job, and one job only, detecting light. So before we follow a single ray of light into the eye, let's take a look at the incredible hardware on the outside that's designed to keep these delicate instruments safe. First up, the eye's protective gear. Your first line of defense, of course, is your eyelids and eyelashes. The eyelids are like automatic shutters, blocking out light when you need to sleep, and every time you blink, they're spreading a fresh layer of moisture across the surface. And your eyelashes, they're like tiny little fences, catching dust and debris before it can get in. So where's all that moisture coming from? Well, that would be your tear glands. They're tucked away up in the outer corner of your eye socket, and they are constantly, and I mean constantly, producing fluid. This isn't just about crying during a sad movie. It's a 24/7 cleaning and lubrication system for your eyes. But here's the really cool part. Your tears are packed with a secret weapon, an enzyme called lysozyme. This stuff is basically a natural disinfectant. It literally destroys bacteria on contact, giving your eyes a powerful shield against infection with every single blink. Amazing, right? All right, so the eye's defenses are up and running. Now for the main event. Let's follow a single ray of light as it takes this incredible journey from the outside world through the eye to eventually become an image in your brain. This journey has 4 main checkpoints. First, light hits the cornea. Then it passes through the pupil. After that, it gets focused by the lens, and finally, it lands on the retina at the very back of the eye. So let's break that down step by step. Now, the eyeball itself is actually made of 3 layers, kind of like a little nesting doll. The outside is the sclera. That's the tough white part you see. The middle layer is the choroid, which is full of blood vessels. And the innermost layer? That's our target, the light-sensitive retina. Okay, so stop number 1 for our light ray is the cornea. This is just the clear, dome-shaped front window of the eye. It's actually part of that tough sclera layer. Its main job is to do the first, most powerful bending of light to start focusing it. And here's a wild fact for you. The cornea has 0 blood vessels. It actually gets its oxygen directly from the air when your eyes are open. Once light passes the cornea, it's gotta stay on track. That's where the choroid layer comes in. This layer is dark, and it works exactly like the black paint on the inside of a camera. Its job is to absorb any stray light that might bounce around, preventing glare and internal reflections. It's a simple but absolutely crucial design for getting a sharp, clear image. But how much light are we letting in? Well, that's controlled by the iris, the colorful part of your eye. It's basically a muscular diaphragm that works just like the aperture on a camera lens. When it's super bright out, tiny circular muscles squeeze the pupil shut, making it smaller. And in the dark, a different set of muscles, the radial ones, pull it open wide to let in as much light as possible. Okay, so after passing through the pupil, the light hits the lens. And the lens has a genuine superpower. It's called accommodation. This is the eye's incredible ability to change its own shape to adjust its focus, letting you see things clearly whether they're way off on the horizon or right up close to your face. And here's how it pulls that off. When you look at something far away, these things called ciliary muscles relax. This pulls on a set of ligaments which stretches the lens out, making it thinner. But the second you look at something up close, like your phone, those same muscles contract. This loosens the ligaments, and the lens naturally bulges into a thicker, more powerful shape. It's happening constantly, and you don't even have to think about it. So, the light has been bent by the cornea and perfectly fine-tuned by the lens. Now it reaches its final destination, the retina. You can think of the retina as the movie screen at the back of your eye, or maybe the digital sensor in a camera. This is where the magic happens. And here it is. This is the big reveal, the answer to my question from the beginning. Because of the way the lens bends light, the image that gets projected onto your retina is inverted. Yep, everything you see is projected onto the back of your eye completely upside down. So the retina's job is to turn this upside-down light image into an electrical signal the brain can understand. And it does this with two types of photoreceptor cells, rods and cones. The easy way to remember it is rods are for night vision. They're incredibly sensitive to dim light, but they don't see color. Cones are for color. They need bright light to work, but they're what give us our rich, vibrant view of the world.
But having an upside-down black and white and color image on the retina isn't the end of the story. Not even close. Now, that electrical signal has to be sent to the brain to get decoded.
Now, not all parts of the retina are created equal. There's a tiny little area called the yellow spot, and it is jam-packed with cone cells. It's the retina's high-definition zone. When you look directly at something to see it in crystal clear detail, you're aiming this yellow spot right at it. But then there's a point that has no photoreceptors at all. This is called the blind spot. It's basically a tiny hole in the retina where the optic nerve, the massive data cable connecting the eye to the brain, leaves the eyeball. So why don't we see a black hole in our vision? Because our brain is so smart that it just takes a guess and fills in the missing spot with information from the surrounding area. Wild, huh? Of course, this incredibly complicated system doesn't always work perfectly. So let's take a quick look at a couple of common focusing problems that millions of us deal with every day. The two most common issues are myopia, which you probably know as nearsightedness, and hypermyopia, or farsightedness. With myopia, the light gets focused too early in front of the retina, making faraway things blurry. Glasses with a concave lens fix that. With hypermyopia, the opposite happens. The focus point is behind the retina, making close-up things blurry. That gets corrected with a convex lens. So when you put it all together, what you have is this incredible biological camera. But the truly mind-blowing part isn't the eye itself, it's the brain. It takes an upside-down, two-dimensional image that has a hole in it, and in an instant it flips it, merges the signals from two eyes to create depth, and presents you with this seamless, rich, three-dimensional world you experience every second. Which leads to one final thought. Our brain corrects an upside-down world without us ever knowing it's happening. What else is our perception filtering